Okay, the question's on page 261, starting with number 38. These are with elastic potential energy. An object is hung from a vertical spring extending it by 24 centimeters. So we're giving you the x, 24 centimeters, or 0.24 meters. And you do have to change these to meters, okay? If the spring constant is 35 newtons per meter, what is the potential energy? So K is 35 newtons per meter. And so our equation is EE is equal to 1/2 kx squared. So 1/2 K is the 35 newtons per meter. 0.24 meters is the x, and it's just the 0.24 that gets squared. And you should get an EE of 1.008 joules. Number 38. Done. Number 39 says, an unruly student, none of you of course, pulls an elastic band that has a spring constant, so it's giving us the K, the spring constant, of 48 newtons per meter, producing 2.2 joules, so EE 2.2 joules, producing 2.2 joule increase in the potential energy. How far? You're looking for x. So again, EE is equal to 1/2 kx squared, multiply both sides by 2, divide by k. So x squared will equal 2EE over k. So 2 times 2.2 should be about 4.4, divided by 48 newtons per meter. So 4.4 divided by 48 should give you 0.09167, but that's meters squared because that's x squared. Then you need to take the square root, and when you do, you should have 0.303 meters for your final answer. Number 40 says, a force of 18 newtons compresses a spring by 15 centimeters. So F is 18 newtons, compresses a spring, X is 15 centimeters, or 0.15 of a meter. And then the question wants to know, by how much does the potential energy change? Before you can find EE, you need to get K. And you can get K by doing F equals KX. So K equals F over X. So 18 newtons divided by 0.15. And you end up getting a K of 6 over 5. 120, I think it is. If I do it right in my head, 120 newtons per meter. And then you go to EE is equal to 1/2 kx squared. So EE is equal to 1/2 the 120 newtons per meter times 0.15 squared. So 0.225 times 60, so 2.25 times 6. Oh, I need to move the decimal one more. 1.35. I have my decimal in the wrong spot because of the squared. 1.35 joules. Elastic potential energy? Done. And now to efficiency. So over on page 270, number 44. We already did the ones in between. They were power. A portable stereo requires 265 joules of energy to operate a CD player, yielding 200 joules of sound energy. So if it requires, it's what you have to put in. So the 265 is the energy in, and the sound is what you get out. It's 200 joules. So efficiency is equal to out over in. And remember I had said if you're not sure, it always has to be the bigger one on the bottom. So 200 joules over 265 joules times 100. And when you do this math, you should get 75.47. So EFF 75.47%, which really isn't that bad. Part B says, where does the energy loss go? If you've ever put a CD in a CD player and then taken it out right after it's turned off, you would feel that it was hot. It's lost to heat. All right, number 45. A 49-kilogram child sits on the top of a slide that is located 1.8 meters above the ground. After her descent, the child reaches a speed of 3 meters per second. At the bottom, calculate how efficient the potential energy is converted to the kinetic. So the energy in is her gravitational potential energy at the top. And the energy out is her kinetic energy at the bottom. And anything lost in between will be due to friction. So efficiency will just be equal to out, the kinetic, over in. Right? So we can find, maybe I'll do it separate, you can find EG, it's just MGH. So it's 49 kilograms times 9.81 meters per second squared times 1.8 meters. Okay, and then the energy out is 1/2 mv squared. So 1/2 49 kilograms times 3 meters per second squared. And of course I said let me do it separate, but I didn't in my own life, so I now have to punch this in and then we'll probably run out of time. 49 times 9.81 times 1.8 gives you an energy in of 865.242 joules. And then you are going to put on the top 0.5 times 49 times 9, 220.5 joules. And when you divide these and multiply by, I lost my thing, by 100, you should get 25.484. 25.484%, because I forgot times 100. Times 100. Okay? So the in is how much energy she has at the top of the slide. The out is how much she has at the bottom. 46. A machine requires 580 joules of energy to do 110 joules of useful work. So if it requires, it means you need to feed into it that much. And if it's doing useful work, that means what you're getting out. So the 110 joules go on the top, and the 580 joules goes on the bottom, multiplied by 100, and you should get 18.9655%. Number 47 says, an incandescent light bulb transforms 120 joules of electrical energy to produce 5 joules. So 5 joules is what you get out. And I think I had said earlier when we were talking about efficiency that it wasn't, light bulbs weren't very efficient. And 120 is what you put in. And so for the incandescent bulb, you have an efficiency of 4.16 repeating percent. Not great. Then it says a fluorescent one, it's still get your 5 joules out, but it only needs 60 in. So it should be twice as efficient, right? 5 joules over 60 joules times 100, and so you get 8.3 repeating percent. Why is the fluorescent one more efficient? Because it doesn't lose as much to heat. Incandescent give off a lot more heat. Number 48, we're going to run out of time. A microwave oven transforms 345 joules of radiation to 310. So efficiency, this is number 47, it's going to go off, is equal to out over in times 100 is equal